Okay. Okay, thank you very much for the introduction, Tina, and thanks to EPNOE Organizing Committee for letting me have this chance to present some of the researches that is going on here at FSCN and Mid-Sweden University. And some of you know where we are located. It's actually in the middle of Sweden, as you might hear from the name, and it's in Sundsvall, which is about 400 km north of Stockholm. And the picture, the photo to the left is a part of our campus in the central parts of Sundsvall, and the picture to the right is what we are surrounded of mostly, since it's an area where we have a lot of forest, and the forest industry is very important for the region as well as for the country here in Sweden. Okay, my title of this talk is Cellulose in Emulsions and Functional Composites, and I thought that we should start with the emulsion part, and then we might need some definitions and some small lecture in things that are relevant and important for this. And I guess some of you might not work with amphiphilic molecules that much, at least you might not think you're doing it, but we'll see. I start. Okay, Amphiphilicity, what is that? If you look in Wikipedia, you can find a definition, which is quite all right, I would say. It comes from Greek, as most of the science words we're using comes from, and amphis in Greek is both, and philia is love or friendship. So an amphiphilic substance is a chemical compound possessing both hydrophilic, which is what we usually call water-loving also, or polar, and lipophilic, fat-loving, non-polar properties. And a typical amphiphilic structure is the surfactant structure that we usually call it. As you see in the picture here, you have a tail where you have this reddish cone, where you all have very much hydrophobic properties or lipophilic properties. And then you have a group, where the head group of the surfactant is usually charged or non-charged, but hydrophilic in some way, polar in some way. So this is what we see, and if we look around us, we are always all day long using this kind of amphiphilic substances to help us to survive in our society. There are many, many examples of this, but some of them are maybe you're using it in your household for instance, washing powder, dishwashing powder, shampoos and soaps and so on. And you need this to transfer the grease, the more non-polar or lipophilic substances into the water phase, since water and oil do not mix generally that well. That's why you need these transfer agents, the amphiphils, the surfactants. And one example of this is also a soap bubble. You can look at a soap bubble and be fascinated from it in many ways. But if you go into a closer look, you can see that the soap bubble is composed of a lamella, a membrane, where you have water. And then you also have some molecules, the surfactants in this case, that are mediating the interface between the water in the lamella and the surrounding air. And in this case, you have two sides of a soap bubble, so you need two layers, a bilayer of surfactants, making this happen. So the surfactants or the amphiphils, they are actually a substance that goes to an interface between a non-polar and a polar media. And it could be air that is a non-polar, and it could be water, or it is water. Usually the polar substance, since water is so common. And then, I mean, it doesn't need to be air. It could be another liquid which is non-polar too. And actually, from a lot of research and also from old, both old, but especially now from the 2010 and beyond, there has been a lot of work looking at cellulose and seeing that cellulose is also an amphiphilic polymer. So that is stated now, even though it's not that outspoken as a surfactant with a tail and a head group, it has a properties that makes it amphiphilic. And that is, you have the OH groups in a certain, if you look at the molecule, the polymer chain, you can see you have OH groups that are sticking out, pointing to one direction, and you have also the CH groups from the backbone of the cellulose that actually is more directed in another direction. So you have both these equatorial and horizontal properties. So you can see it if cellulose lies down, it has one property at the end, at the edges, and another in the plane. And this you can use when you do emulsions, and you need to use it in some way. So emulsion is a good example of a trick to make oil and water mix. And to make an emulsion, you need the water and the oil, and then you need something more and a lot of mechanical energy usually. So you need something that mediates the interfacial energy or interfacial tension between the two liquids. So something that is both polar and non-polar, that makes the energy go down at the interface between the phases of the different liquids. So that's how you get your mayonnaise. You need something more, and we use in mayonnaise, I mean, it's not the least compound, but it's a quite major compound. It's an egg yolk, and in the egg yolk you have these emulsification properties coming from the lecithin, which is a protein that, and proteins are always amphiphilic, and a bit depending on which pH you have, you get it to be over or under the isoelectric point, and then you can give it some different properties that makes it more or less amphiphilic. And if we look in the history, we have a lot of cellulose-based emulsifiers. Actually, we have, for instance, these cellulose ethers that have been used for that purpose also. And there are plenty of them. You have methyl cellulose, ethyl cellulose, hydroxypropyl cellulose, and HPMC, and plenty of other combinations. And you can also actually use cellulose in other forms if you go into particle emulsifiers. The first ones I mentioned is the molecular emulsifiers, the polymeric ones. But you can have solid particle emulsifiers also, and then you go into a special class of emulsions, the Pickering emulsions, that are named after the discoverer of these ones. And then you have particles which have also gotten some properties. For instance, on the cellulose nanocrystals, you have planes where you have more hydrophobic properties and planes where you have more hydrophilic properties. And if you have a good tuning of this sort, sometimes it happens naturally, you will have them as an interface or a facial layer onto, for instance, an oil droplet in water. cellulose nanofibrils works a bit differently, but they also have this, but they are so much bigger, so it takes too long usually to get them into the coverage state, since the diffusional processes are slow, but they still contribute, and they also of course change, for instance, consistency. I mean, you get into a completely different viscosities and rheology properties, which makes the emulsion to work. And you can of course do regenerated cellulose particles also in the same way as you use more or less nanoparticles that are natural. You can make your homemade solid particles by regenerating dissolved cellulose or making small microgel particles that can contribute to the emulsification process. And this is quite important, since usually we need emulsions in many cases, and since we're surrounded with water, and we need sometimes oils to be in some way mixed and transport in this system, we need to do these emulsions, and to have and use as natural as possible emulsification agents like cellulose, which is maybe one of the the most natural that we are working with in Epinoe community. It is very nice to more go into the details how it works and why it works. And cellulose, since it's amphiphilic, it should be able to make emulsions, and that is what we have tested a bit. And the applications areas are very many. I mean, first of all, if you look at from the left here, cosmetics and personal care may not be that important for some people, but very important for others. Foods, you might see a lot of different applications. I mean, the mayonnaise is one thing, and I don't say that you use cellulose there, but as an example of application areas, you can do other kind of functional foods and so on. And in pharmaceutics, there you have a lot of cellulose, and in these kind of different delivery systems you use it, but also as different kinds of rheology controlling agents. And in paints and coatings, they are important to make these oil and water to mix good. And hollow microspheres you can make from these kind of emulsions, and foams. So drug delivery carriers in biomedical applications, microreactors, catalysts, sensors, supercaps, fillers, and rheological modifiers, packaging material, and so on when going to foams, for instance. What do we use then? Yeah, in our research, we're going from the forest, as I started with here, going into cellulose pulps. And then there are these cellulose emulsifiers, for instance, the derivatives like the ether compounds, which you get directly from the pulp via chemical reactions. It's usually a solid state reaction, more or less, and then you get your ethers afterwards. But you can also go this way via the nanoparticles like the CNC, the strong acid hydrolysis, and mechanical treatment, and some other treatments before to get the cellulose nanofibrils. Or, as I said, dissolution and regeneration. But we have chosen to look at the cellulose from a molecular state more, just since it's interesting also to learn more about these amphiphilic properties and really prove them, and then we have used them. So we have been using cellulose solutions that we have made in water-based solvents, which is sometimes only sodium hydroxide when it comes to lower molecular mass cellulose, but also sodium hydroxide urea and acids in some way. And one of my former PhD students, Dr. Carolina Costa, who recently actually defended her thesis here in October, she has been worked a lot with this. And if we look at some things that relates to these interfacial properties, which tells things about cellulose amphiphilicity, we can look first to the left on the acidic media, where we have used phosphoric acid, which is really harsh conditions to dissolve cellulose. It works quite well, but of course you have an aging effect. And the aging effect in this case makes the depolymerization take place. And here Carolina studied how the interfacial tension was actually how it looked like at different stages for these cellulose solutions. So if you look at the bluish turquoise dots here, you can see only the solvent, which is the hydro or the phosphoric acid, and it starts immediately at about 45 millinewton per meter as interfacial tension between the oil and this solvent, and it goes down to some state here a bit below 35 if you wait for a while. If you put in cellulose in this solution, this acidic media, you will see when you measure the interfacial tension, you will see a significant drop. And this significant drop is due to, of course, that the cellulose has a lowering effect on this interfacial energy, which makes it go to the surface between oil and water, or oil and acid, to lower it. And that tells a lot about its amphiphilicity. And here you can see that if you age these solutions, this acidic solution, you will actually get lower values. So at 360 hours aging, you get the lowest curve here. Also the initial value is lower. If you go to another part, yeah, you can see that it drops. And if you go to another media, the alkaline media, it's a bit more tricky. So we have used a bit of sodium hydroxide-based solvents here. And there is another zero line, you could say, for the solvent itself when it comes to the interfacial tension. It's also another method of measuring here. It's a Wilmy plate here and a pendant drop in this case. And then you have, if you put in cellulose in sodium hydroxide, you can see it reduces a lot, or a lot at least significantly. So you can see here, also here cellulose shows its amphiphilic character. If you have urea and cellulose, you will even get further down in the IFT, but then you have in some way change your solvent a bit, since it's a sodium hydroxide urea solvent, and urea in itself, what it's argued is that it's a slightly hydrophobic molecule in the way that it actually helps cellulose to dissolve. And that makes also sense when you look at the IFT, that it goes further down. So in the first curve, actually you have both sodium hydroxide and urea has in the more or less the same line here as it's represented by the bluish curve. But here when you have cellulose and sodium hydroxide urea, you get even further down. So if you look at how these different, or how these emulsions look like, so in this upper picture, we don't have more than the solvent and oil and mixed it a lot. And then you cannot really say it's an emulsion. It will at least phase separate macroscopically very, very fast. So there are very big domains of oil that already have either not been really mixed, or have already very rapidly been coalesced together, the oil droplets. But in the lower picture, when you add cellulose, you will get these kind of emulsion droplets swimming around in the surrounding solvent. So inside these droplets, you have the oil, and the surrounding the oil, you have adsorbed cellulose on the droplets. And there could also be some other spare cellulose surrounding, or as a matrix here in certain extent. Since everything is not covering the droplets, it's a bit more than that. We will see later. So if we look at what I earlier mentioned about the molecular mass and how it influences, so the aging in acidic media is quite radical when it comes to molecular mass. So we did a study where we looked at how the original cellulose was when it came to the molecular mass distribution, and how the different aging times changes these distributional profiles. And what you see here is that you go to lower, if you look at the peaks, you can say you go to lower peak molecular mass, but you can also see that the distributions are getting a bit more narrow, actually, since you cut away a lot of the larger ones, and you start to get into some kind of more, I wouldn't say steady state, but at least you get into more of the same in a way. And if you compare a bit with other kind of cellulose derivatives, you can see a bit about the explanation of these interfacial tension changes that you get when you have high or low molecular mass of the polymers. And this is HPMC. And if you have high molecular weight, you will not really go down that far as you have with low molecular weight. And this is dependent a lot on how fast a molecule can be transported or diffused throughout the solution. And a smaller polymer chain is of course much faster than the larger one, which also makes it faster to both to cover the surfaces or the interfaces, which means that the interfacial tension goes down faster and to lower values with low molecular weight polymers. If we look at the alkaline media, we can see that there is a very, very important thing with the solvent quality here. If we use 3 different solvents, for instance, sodium hydroxide and sodium hydroxide urea and TBAH, we will see different curves here when it comes to the interfacial tension. So sodium hydroxide based solvents, which means both sodium hydroxide and urea and sodium hydroxide, they lie quite high. If you put in cellulose, we went down as we saw earlier, and yeah, and so on. But if we have the TBAH, we have very low interfacial tension, and that the explanation for that, I mean, you don't see that much difference if you have cellulose here. It's more or less the same curve. You can see that there is 2 curves here, and it's more or less overlapping. But the TBAH ion itself, TBA ion itself, it is amphiphilic, so it will contribute to lower the IFT a lot. So it's not really comparable, but it also tells a bit about different kind of processes in these systems that are competing with each other, which makes it sometimes hard to make emulsions, since you have another kind of solvency for some of these species. So the solvent itself is amphiphilic in the case of TBAH, which makes cellulose to lose a bit of its contribution, you could say. But that also tells us about the which is the best solvent for cellulose here, and it's actually goes with this amphiphilic character of the solvent, different solvents. So if we look a bit more on the cellulose in its dissolved states, how it's able to stabilize oil and water emulsions, we can look first on this acidic media. We can, if we do this emulsification, we will have a metastable dispersion, which looks nice immediately, but after about 24 hours, we can see that it has an oil layer on top of it here in the picture. So it's not stable for so long. And that is, of course, due to several things. One is steric stabilization. Another thing is that you don't have the affinity to the surface that hard, so you will lose oil. The oil will leach out, you could say, from the oil droplet, and you can soon have different kinds of escaping that makes a bit of a macroscopic phase separation possible, larger lumps of oil together. But if we go further on and start to make this solution a bit higher pH, it's actually enough with putting in some water into this acidic solution. You could also put in some sodium hydroxide, but water is enough to dilute it a bit. Then you lose the solvency, and the cellulose is actually regenerated onto the interface between oil and water. So you get small oil capsules, you could say, in water. So then you also get a quite or an excellent stability to this macrophase separation that we saw in the previous image. This can actually stay for a very long time, extremely long time, years, without giving any phase separation. And you also see a decrease in the drop size and polydispersity of these particles. But you still have a flocculation or creaming, so you don't really have the perfect stabilized, you don't have the stabilized from the point of view of colloidal stabilization between these particles. You will find a creaming, but anyway, it's possible to stir it and have a homogeneous emulsion also. So what happens when we do this acidic hydrolysis of these cellulose that we use for these emulsions, that is that you get smaller droplets also. You get smaller molecules and smaller droplets, and that makes sense since you have higher speed or higher velocity or diffusion of these smaller ones. So it's easier when you're mixing, it's easier to cover oil droplets before they come together. So if we go to a bit of the alkaline media, we can see differences between these cases. The upper case with sodium hydroxide, and then we have sodium hydroxide urea, and then TBAH. And if we carefully look at our samples over time, we can see that the first and the second one, the sodium hydroxide and sodium hydroxide urea, looks the same, more or less, but the TBAH doesn't really show any signs of an emulsion from the creaming, or what you could call it here, the light scattering, I would say. And if you wait some while, you will find that there is a creaming layer here on top of the alkalines, both for the sodium hydroxide and the one with urea. And if you wait even longer, you will see that the urea case, you will start to find some more macroscopic phase separation, but not only in the sodium hydroxide solution. In the TBAH, you immediately see the macroscopic phase separation taking place. So you have an oil layer above the water layer here. So that tells a bit that you really dissolve cellulose too much, so it cannot really stay at the oil droplets when you use TBAH. So it's not possible. It's too good solvent for cellulose to go to the interface. So if we take our samples and start to play with the solvent quality in the way that you can do when you change the pH in a way, you decrease it very, very little. So you have your samples in the alkaline media, both the sodium hydroxide urea, and the TBAH, and then you decrease pH similarly in all these cases. You can see that you start to have a bigger creaming layer, larger creaming layer when you go down. And if you go down further, you get even more creaming, which tells that you actually, you have a better opportunity to make these, make more of the more particles, I would say, in where you have the oil encapsulated, or more bigger part of the emulsion of the total volume. The same goes with the sodium hydroxide urea, but in the middle test tube here, you also see that you can end up with some aggregates of cellulose. If you do it in TBAH, you really don't see that much. Actually, in the test tube to the right, you're not really having a creaming layer, a real creaming layer. You also have oil on top. It's just very, very unstable for the emulsions. So it's hard to reach, even though you do the same changes in pH. It's hard to reach this at all with the TBAH. You will only go, you will go far away from creating a good emulsion. But the important thing here is that you cannot have too good solvent. You need to have a solvent that is balancing solvency and non-solvency, you could say, to create this in the alkaline state. We can look how it looks like also when you check samples where you don't have any oil on the top here. You can see background polarizing or microscopy pictures of cellulose, so that has been regenerated. And in TBAH, it's not that easy to see, but you can see they are there also. And if you do the emulsions and regenerate them, you can see at these arrows and at more places, you can still see these oil droplets covered with cellulose. But in the case of TBAH, you don't really see it. It's a big lumps of oil instead. It's not really droplets anymore here. And if you make it a bit more visible, you can point out the droplets even better with these red circles. If you go further looking at this in a microscope, a cryoscanning microscope, electron microscope, you can see the particles or the actual capsules with oil and cellulose shells in the acidic and also in the alkaline emulsions. And here in the alkaline emulsions with this technique, you really also see how the cellulose is surrounding the oil here. And then you have some more cellulose in the matrix everywhere, but you have your oil droplets covered with the cellulose. We just make a summary here. We can talk and say that the restricted solvency of cellulose in water is actually the most demanding thing to make cellulose, or if I call it native cellulose, non-derivatized cellulose to be used in emulsions. So you can only go to this extreme pH if you work in water environment. And it works well under acidic conditions. And you can make this regeneration, and then you can do oil-filled capsules, for instance, if you would try to do other kind of applications that are long-lived. And after this regeneration, you could also do a pH neutralization. So that makes it very good from a perspective of non-toxicity, since you don't have any strange chemicals. If you do the neutralization, you will get salts that you can wash away, so you don't have any other kind of dangerous chemicals involved, which might be very good for some applications. If we go to the alkaline conditions, the solvent quality has to be carefully balanced, as you saw. So there is a trend with the solvent quality, and then you have a trend with the cellulose affinity of the oil-water interface between these different solvents, and you need to find a good balance here. And when it comes to those one who works, sodium hydroxide and urea, it means that you need to play a bit with the pH to make these emulsions work well. Okay, then I thought we move on, still going into cellulose, but into more composite world and different kind of composites that you can make if you utilize, for instance, these water-based solvents. It might be possible with other ways, but we have studied cellulose dissolution in water-based solvents, and usually we use either lithium hydroxide and urea and to dissolve it, or sometimes sodium hydroxide urea. And the idea with this has been to, for instance, to be able to make mixtures with other materials, to do these composite materials without any type of chemical reactions involved, not necessary at least involved. So if you have cellulose in these solutions, and then you have polymers or particles that can be dissolved in the same way, or particles that can be dispersed, and then you mix them together, you can get these kinetically stable mixtures, which of course, if you wait, they will phase separate. But if you want to do something with them, you have quite a lot of time to do it. So if you just mix them and do your trick, you can produce different kind of a lot of different kind of co-regenerated functional cellulose nanocomposites. So you can make films, you can make particles, you can actually, in this case, it's graphite, nanographite and cellulose material, which is conducting and so on. And so that is quite interesting. Yeah, it's more or less your imagination that restricts you from what you can do usually here. And we have done a bit of that. For instance, we tried to use two different polysaccharides, cellulose and chitosan, and made some particles in different sizes. So, for instance, here we have a macro particle preparation. It's not as fancy as it might read. It's only having cellulose solution and dripping it into an acidic chitosan solution. Here chitosan is very soluble, and here in this lithium hydroxide urea cellulose is very soluble. And if you drip it, of course, you get a regeneration and you get chitosan incorporated in the particles. And if you wash them and go further and make them into this solid material, you can see them here. They are quite big. They are macro particles. They are, yeah, some millimeter and a bit beyond 1 millimeter, or maybe sometimes a bit beyond. But anyway, you can see them at least. And if you look closer to them, you can also find that you have like this kind of areas which tells us, if you go further to the chemical analysis later on, that you have a shell structure, you have a core shell structure. So you have chitosan on the outside and cellulose internally, of course, since you do drops with cellulose, but you still have a coverage of chitosan here. And the structure you get, if you go and look, it's quite porous structure. So this was type A. And then you can do type B and C. And type B is actually utilizing the same procedure, mixing them together and putting in a cross-linking agent, and then making a water in oil emulsion, where you do a regeneration by changing the temperature to 60 degrees from the low temperature here, where you have solubility, and then you go to a higher temperature where you lose the solubility of both these polysaccharides. So inside these water droplets in the oil, you also get this reaction between the cross-linking agents and cellulose and chitosan. And you go further and prepare the solid particles, and then you get much smaller particles, first of all, and they have a structure that you can determine in a way of porosity and look at. And if you then do another route, you take away the cross-linking agent and do the same procedure. You can actually make the same kind of particles without any cross-links. And then you get this kind of physically cross-linked ones that you get due to this intermolecular mess that you will have. You will have the polymer chains intermingled and regenerated together.
Magnus,
yep.
would be great to round up soon so that we will have some time for questions as well.
Okay, okay. I ran away and then I show you these more analytical results that you can see. For instance, the blue curve tells a bit about that you have your cross-linking agents here. Further on, we can do this, of course, to make cellulose chitosan composite films also, which really the trend in the strength, if you look at the tensile strength, is that if you lose or if you increase the chitosan content, you will go down in strength. So, but still they work as films. And in this study, we checked how the swelling was actually changing when we had this chitosan incorporated and played a bit with pH, and it also tells that the thickness is also changing, and it also tells that if you go into low pH, you can see release of the chitosan. Another way of utilizing this is to do hybrid materials, mixing this more or less in the same way together and regenerating. And then you can use the cellulose as template for the growth of these nanoparticles. And you can do a more traditional way of incorporating the nanoparticles and make films with these. The last thing that I wanted to tell you about is the triboelectric applications that we're working with these films, especially of regenerated cellulose. And I mean, static electricity is not a strange thing. It has been known for ages, but in the last couple of 10 years, it has been developed a lot, and actually it comes, this triboelectricity comes from frictional events that we know, and it is due to electron transfer between different materials. And non-conducting materials are especially outspoken, so that is interesting. So it works like this: rub your balloon, and then you get another charge on the balloon, and then you can actually put it on a wall, and there is an adhesion, which also explains a lot of adhesion phenomena that once thought had other origin earlier on. And polysaccharides have these dielectric properties. And if we go into what the Teng does, it's actually two surfaces that can, in this way, in a contact separation mode, be put together in a certain frequency, and then you get a charge transfer. And if you have a circuit, you can get electron transport, a current, and there is a voltage, of course, between these. Key factors that are important here is the surface charge density that you can reach in this way, and the contact area between the triple layers. And water can be really bad, or it can actually be optimized. It's not bad if it's in a controlled amount. At Mid-Sweden University, we have worked a lot with these the recent years in different ways, and so one of my collaborators, Renwing Zhang, has done a lot of work here. And recently we did the work with these cellulose films together with him, and found out that at certain conditions, cellulose can be extremely interesting. It's a very high output power you can get from it. And I will end up with showing you a bit of a demonstration of what Renwing did in this paper, with showing how it works. So you can light up this exit sign just by clapping these cellulose surfaces together. It's quite interesting, or astonishing in a way. Okay, thank you very much. I want to thank the gang here at FSCN who are working with the cellulose, but also the tribo materials, and also Professor Song-Ling Wang, who is guest professor nowadays here. Okay, thank you very much.
Thank you, Magnus. Thank you for this beautiful presentation and beautiful work. We are ready for discussion, so I invite you, audience, to ask questions. You may either ask them directly or you can post them in the chat.
May I start? Maybe.
Go ahead, Pedro.
Yes. Thank you very much, Magnus. Very nice presentation covering aspects of dissolved cellulose, making composites, combining particles, films, and so on. Very nice. My question is, I have many questions, but one of the things I found interesting is when you are working with different solvents for the cellulose, when you have sodium hydroxide urea, and then TBAH, and then you show this effect on interfacial properties, right? The question for me is, what is the concentration of the cellulose there in all the solutions? And if you have any aging, for example, of the solution, in case, for example, of the dissolution with the TBAH.
Yeah, we in our studies we haven't really focused on the solvents from the perspective of how cellulose reacts, more than that we already knew from the beginning that acid hydrolysis is very crucial. Mm-hmm. Of course, there is an aging effect, but it's not that outspoken in alkaline solvent as in acids, of course. And when we did these studies on emulsions, you saw very clearly the effect, especially in the acidic media, how it changed. If you have a solution of cellulose in phosphoric acid, it is degraded, and if you use it at different times for doing the emulsions, you get very different sizes of the droplets, which actually is good when it comes to emulsions many times, since you get better emulsions when you didn't have too big molecules. Usually we use around 0.1 to sometimes a bit higher percent cellulose, so it's not that much you need to do the emulsions. And the oil amount is 5% or something like around that. 10 sometimes, but it's not much cellulose you need to do it.
Okay, so you are working with lower concentrations, yeah?
Yeah, when it comes to the emulsions we do, but when it comes to the composites, we have worked a lot with about 4% of cellulose.
Yeah. Okay. Yes, thank you. I left space for other people to ask. Thank you very much.
Thank you. There is a question in the chat on the Triboelectrics. Yeah. What amount of electrical power can you generate with these Tribo systems? Is it enough for example, lighting a home?
It's direct. If you look at the triboelectrification alone, it's a direct output. So as soon as you have this frictional contact, you get the output. And if we look into cellulose, our record or our world record right now is 300 watts per square meter. But you should also be aware of that. It's not completely proportional to surface, so you can scale up. I mean, if you have several smaller units, you will get more than from one bigger unit. But what I would say that you could, if you combine the triboelectrics with the for instance, a supercap or something that is good in catching the high output immediately, then you could, if you walk on a floor, you could power lights. If you have the triboelectrics in the floor, you can walk on the floor, then you could light up the corridor. But I mean, it could also be used as in other ways, but as a main contributor of electricity for your home, it's not really that application.
Yeah, it would be challenging to maintain the lighting, right? Yes.
Yeah, I think we would be very thin or something like
Yes,
that.
it is an opportunity. It's an opportunity. There's one more question we can take in the chat. Sumit is asking, can you please comment on thermal stability of virgin regenerated cellulose films and the composite cellulose films?
Yeah, they are quite stable. You could go into about 200 degrees at least, and we have done a lot of experiments with putting metal on top of cellulose, also for other applications that we are working with. But then you don't melt the metal, of course. You do other, but it's stable for quite a long time. I mean, 200 degrees is not the problem if you don't store it for too long, at least. And then depending on what you put in the film as the other component, it also restricts, of course. But I mean, no, not the big thing. I mean, cellulose doesn't melt, but it will start to carbonize after a while.
Yes. It's a challenge we all know.
Yeah.
Great. I will close this session now. If there are any other questions that you may have for Magnus, I'm sure that you're willing to take some email communication afterwards.
Yeah, absolutely.
Great.
Thank you.
Thank you for your contribution.